Good day. My name is Khoto Mademucha, and I will be explaining quantum computers alongside my group. Now, what is quantum computing? The description is that it is a multidisciplinary field combining physics, mathematics, and computer science components with you alongside quantum mechanics to resolve complex problems beyond the current scope of supercomputers. This is achieved with the use of qubits instead of regular bits. The components to quantum computing are superposition, which allows quantum computers to create and represent different bits and pieces of information. Entanglement, that happens when a link shared between two systems allows for shared access, meaning that when you know one, you can gain the information on the other. Decoherence, which is when a quantum state collapses into a non quantum state, which allows for interactions with classic computers, and interference, where possibilities can be produced and interacted with entangled quantum states. Now we will be looking at contributions and potential contributions that quantum computing has and can make. We can start with the healthcare. Within healthcare, there are projections of quantum computing providing great boons when used alongside classical computing. And these projections have shown to be essential in aspects such as diagnostic assistance, precision medicine, and pricing. Now we look at finance and banking. With the finance and banking is aimed at accelerated trade operations, data processing, and transactions with an ever expanding pool of data and the increasing magnitude of orders. There, there is a requirement for a more accurate calculation and processing of systems. Companies such as JP Morgan, Chase, Barclays, and the Commonwealth Banks of Australia have begun adopting and investing in quantum computing models to more efficiently conduct operations. Tech giants IBM and the software firm 1Qubit have been at the forefront of the current quantum computing trend, with IBM's quantum network having signed research agreements with companies such as Barclays and Cleveland Clinic, and 1Qubit's adaptive approach attracting companies such as Biogen and NatWest, just to name a few. Now we'll be talking about the S curve. With the S curve, due to the due to how recent quantum computing is, it has entered the early adoption phase due to investments by large companies and the agreements that have been signed by these quantum computing firms and companies alike. Now, looking at breakthroughs and challenges, when it comes down to breakthroughs have been made by large companies such as Goldman Sachs and Crown Bioscience in the in the sense of adopting strategic partnerships and agreements in order to explore quantum computing's capabilities and capacities. When it comes down to the challenge, a few such as error correction and scalability have been identified due to the error correction having uh, dealing with the sensitivity of quantum computers and the lack of standard correction techniques, and with the scalability having the seeing that quantum computers still scale low as compared to regular supercomputers. Thank you. I will now pass it over to my colleagues.
I will be speaking on Porter's five forces applied to quantum computing. The first force I will talk about is the threat of new entrances. Quantum computing is still in the early stages, despite growing interest. Building and maintaining these computers is costly due to specialized hardware, cooling systems, and complex supply chains. making entry difficult for competitors. Quantum computing requires expertise in advanced mathematics and physics, limiting the number of qualified professionals. Early pioneers may hold patent restricting access and further complicating development. The next force will be the bargaining power of suppliers. Few suppliers provide critical components for quantum computers, giving them strong bargaining power. Switching suppliers for key components would require redesigning and retesting, leading to profit loss. Suppliers may integrate with businesses, making companies highly dependent on them, meaning that those suppliers have a huge amount of bargaining power, the bargaining power of buyers. Quantum computing is still in the research and early adoption phase, lacking standardized hardware and software. Early adopters and research institutions influence the features of quantum computers. Initial buyers will likely be large institutions with demanding needs, giving them strong bargaining power. The threat of substitutes. Classical computers keep improving, enabling them to handle large computations at lower costs than quantum computers. Quantum computing remains a niche, research-focused market, making profitability challenging. Emerging disruptive technologies like optical and neuromorphic computing could potentially replace quantum computing or make it less, worth pursuing. Industry rivalry. There is intense competition to develop the fastest, most advanced quantum computer. Government labs and major companies like Microsoft are leading efforts to improve qubits, fix errors, and create better algorithms. Some companies use strategic alliances and collaborations to share knowledge and speed up progress. This heightened competition further reduces profitability in the industry. And with that said, that's all the five forces explained. The next will be the race towards a dominant design. A dominant design for quantum computers has not yet emerged. The field of quantum computing is currently highly experimental. There isn't a single widely accepted architecture for quantum computing. However, a recent advancement towards a dominant design has been made by Microsoft with their Majorana 1 processor. The Majorana 1 processor is the world's first quantum processor by topological powered by powered by topological qubits. It uses a topoconductor, which is a topological superconductor. There are other competing designs, however. These are photonic qubits. These qubits use light particles to encode quantum information. Neutral atoms. This approach uses neutral atoms held in place by patterns of light. Trapped ions. Uses individual ions held in place by electromagnetic fields. And then there's superconducting qubits. This approach is currently the most researched and uses qubits created by tiny superconducting circuits.
Good day, my name is Martin, and I'll be taking you through the SWOT analysis for quantum computing and its diffusion of innovation. The key advantages of quantum computers include the following. Quantum computers have exceptional processing power that allows them to do complex calculation exponentially faster than classical computers, such as in molecular simulations. They also have a higher problem-solving capacity that allows them to solve problems that classical computers cannot solve. Their existence produces the potential for further innovation by using its incredible processing power. Tech companies like IBM have shown lots of interest in the technology and has resulted in the technology receiving financial investment. The main weaknesses of this technology lies in how limited its accessibility is at the moment. The following are a few risks and limitations of quantum computers. Given that quantum systems are highly sensitive to noise and are prone to quantum decoherence, error correction techniques are required. Their technical complexity makes their hardware difficult to manufacture and maintain, requiring specialized environments to function. Programming these computers requires specialized knowledge, which greatly limits the software ecosystem. Given how difficult it is to manufacture the hardware, building large-scale and cost-effective quantum computers is still an engineering problem that has not been navigated. The potential of quantum computers allows the technology to present a fair number of opportunities, such as the disruption of multiple industries leading to more innovation, the chance to develop quantum-resistant encryption, improving security, running advanced simulations that could lead to the development of new discoveries in various fields. If more governments and corporations show interest, research and development may accelerate. However, there are some threats that come with quantum computing, such as technological limitations delaying its adoption to the general public. And given how complicated they are to develop and use, it is unknown if full-scale use of quantum computers is feasible. If countries decide to be competitive with this technology, this may lead to their misuse and hesitation to collaborate in improving quantum computers. Overselling the technology may cause investors to stray away due to how unrealistic it may sound. E.M. Rogers' diffusion of innovation theory applies to quantum computing, exploring how it's being adopted, the challenges it faces, and how we can accelerate its spread. Rogers' theory outlines how new technologies spread through society in five adopter groups: innovators, early adopters, early majority, late majority, and laggards. Applying this to quantum computing helps us understand its current adoption landscape and identify future opportunities. Early adopters, typically tech leaders, research institutions, and governments, are willing to take risks and invest early. For example, IBM launched the Quantum Experience in 2016, giving global users cloud access to quantum processors. This move democratized access and built credibility on the technology. Now, the early majority, more pragmatic sectors like finance and pharmaceuticals are joining. JP Morgan Chase uses quantum for risk modeling, while Roche explores it for medical discoveries. Even with all its potential, quantum computing faces real challenges that are slowing down adoption. First, the technology itself isn't fully mature, which leads to high error rates and low stability. Then there's the cost. Quantum systems need cryogenics and specialized environments, which are expensive to build and maintain. A major hurdle is the talent gap. We simply do not have enough trained professionals with quantum skills right now. Security is another concern. Quantum computers could eventually break today's encryption, but agencies like NIST are already working on quantum resistant encryption to stay ahead. And finally, there's uncertainty around return on investment. Many companies are hesitant to invest without clear short-term applications or profits. To speed up the spread of quantum computing, we need some smart strategies. First, we need to educate and upskill. That means supporting quantum programs in universities and creating accessible online learning options. Next, we should encourage collaboration between government, academia, and industry. These public-private partnerships can share resources and drive innovation faster. Making quantum more accessible through cloud programs like IBM Quantum or Azure Quantum is crucial. Open source tools also let more people experiment and innovate. And finally, we need standards, things like common interfaces and protocols so that organizations can smoothly integrate quantum into their existing systems. So, to wrap up, Quantum computing is still in its early days right now. It's being led by engineers, researchers, and governments who are willing to take risks. Yes, there are big challenges, technical issues, high costs, and a lack of trained talent. But the potential advantages are just as big, and that's what's driving progress. If we take a coordinated approach through education, partnerships, and open access, we can help quantum move from a niche innovation to a widely adopted technology. Thank you.